Good afternoon, dear colleagues. Thank you for the honor of participating and speaking in the meeting today. I present the results of the 4 scientists listed here from Russia, Moldova and Romania. The topic of the report is a new approach to monitoring, analysis and forecasting. The application of this approach to the coronavirus epidemic was discussed at a similar meeting 2 months ago. Today we will discuss the approach as a whole, its concept and architecture, the possibilities of its application to various problems, including arms control. We are grateful to all colleagues for a fruitful discussion of the previous report. Thank you. In the previous report, this approach was called the lost opportunities model. Robert Schoch advised us to change the name a little. We gratefully accepted this advice. Of course, in fact, lost opportunities always imply new opportunity. And vice versa. Both are just 2 sides of the same coin, but the new name is more positive. The basic concept of the approach came from a project called Sensitive Home. The aim of the project was to research and develop technologies and solutions for the supervision of an arbitrary set of home equipment. Let's look at the components of the approach. Supervised objects are a set of equipment monitored by the system. The primary data in the system are sequences of time-value pairs. Primary data are generated by sensors that measure certain parameters of supervised objects. Secondary sensors are software modules that input some sensor data and generates secondary data. These are also sequences of time-value pairs. Secondary sensors perform some computation, for example, smoothing, moving average, cumulative counting, value classification, etc. The most important technology in the project is behavior analysis, that supports the classification, typical and untypical behavior of supervised object. Let us explain this. For each supervised object, we find a small number of key parameters that well-defined object state and behavior. The key parameters are represented by primary and secondary sequences of time-value pairs. For example, let us have only 2 key parameters x and y. If everything is well done, then there is on the phase plane x, y a certain domain of valid values of key parameters that corresponds to the concept of typical behavior of the supervised object. Sometimes this domain is just a curve, for example, when in nature there is a functional dependence between x and y. In general, the domain defines some relation between x and y. The choice of key parameters and finding of its valid values domain are, in fact, the stage of system creating and learning. After this, we can do the following. Analysis. We can investigate the properties of the relation between x and y. This often allows us to estimate the characteristics of the supervised object. Monitoring. We can keep track of the point on the phase plane. This allows us to recognize 2 cases: the supervised object has typical behavior or something went wrong. Forecast. We can make predictions about the future state of the supervised object by watching the movement of the point x, y. Sometimes even we can predict in advance when something will go wrong. Monitoring forecast drift. If we make the forecast constantly, then we can watch how our forecast changes. We can watch the forecast drift. It allows us to understand the direction of development of the object, pessimistic or optimistic. Let us look at a simple example of a supervised system that consists of a home and a diesel heating boiler that heats the home. Let us install a sensor to measure the power consumption W of the boiler. This graph shows the primary data. The x-axis is the time t. The y-axis is the power consumption of the boiler. Let us program a secondary sensor that converts the primary data, T, W, into a classification, T, S, where S is the state of the boiler. The variable S ranged over the finite set of boiler states. In the picture, we see two states. Green means fuel burning and heat carrier circulation. Blue means only heat carrier circulation. Of course, there are other states of boiler including abnormal states, but now we discuss only this two. Let us introduce one more secondary sensor that calculates alpha, the fraction of burning fuel time. Parameter alpha is the heating intensity, because the amount of heat supplied to the home per unit of time is proportional to alpha. The parameter alpha can change due to the following three reasons. Changes of outside temperature. Changes of boiler efficiency. I mean any damage or degradation of the boiler. Changes of the thermal insulation of the home. For example, someone forgot to close a window. The first reason is natural, but the other two are alarming and require the attention of the housekeeper. Let us install our outdoor thermometer to have a sequence of time-temperature pairs. On the phase plane, temperature and heating intensity, it is possible to build a domain of valid values that corresponds to the normal efficiency of The boiler and the normal thermal insulation of The home. The relationship between these parameters is expected. More severe frost on the street leads to more intensive boiler operation. Now we can do analysis. We can investigate the relationship between the parameters and estimate the efficiency of the boiler and the home thermal insulation. Monitoring. Tracing of the point, temperature and heating intensity allows us to classify cases the heating system is working properly and something went wrong with the boiler or with the home thermal insulation. Forecast. We can make predictions about the future states of the system monitoring the movement of the point. In particular, we can calculate in advance when the point leaves the domain and something goes wrong. Forecast drift. Making predictions constantly, we can watch how our forecast changes over time. This allows us to understand whether the heating system is developing in a pessimistic or optimistic direction. It is all. In conclusion, let me emphasize that we showed in the project Sensitive Home that this approach can be successfully applied to a wide range of home equipment. So, a certain level of the approach universality has been confirmed. Let us discuss our previous report about the coronavirus epidemic. In this work, my co-authors made key contributions to fill the layout of the approach. Their domain-specific knowledge was the most important to found that. Two key parameters of the epidemic are the number of cases V and its 7 days average velocity VV. Typical behavior of an epidemic is the movement of the point V, VV along a parabola on the phase plane V, VV. Any significant deviation of the point from the parabola is an abnormal development of the epidemic. The deviation can be either pessimistic or optimistic. The reasons can be any new strains, setting or cancelling of antivirus restrictions, responsible or irresponsible behavior of people, mass-intensive vaccination, and any others. The development of the epidemic can be described as the movement of the point on the phase plane along a small set of parabolas and transitions between them. These parabolas are easy to compute. These parabolas are new opportunity and previous opportunities. I mean the opportunity for the epidemic to follow some parabola and complete it. All other aspects of that work fit into the general outline of the approach. We read primary data from the web. The first layer of secondary senses calculates 7 days average velocities of primary values. We perform modeling daily, according to the approach. For the current date, the second layer of secondary senses calculates the parameters of the current parabola on the phase plane. Then the parameters of the approximation by hyperbolic tangent on the plane, time number of cases, are calculated. The third layer of secondary senses calculates a forecast of all values for timestamps in the future. The fourth layer of secondary senses calculates the key events of the epidemic, the dates of these events and their values. Monitoring of the changes in these dates and values allows us to understand whether the epidemic is developing in a pessimistic or optimistic direction. The system is applied to statistics for Russia, Romania, Moldova, and Campania in Italy. What is important, the system warns in advance about a new peak in the burden on the healthcare system. This gives time to mobilize resources. The parameters of the warning are updated daily. Finally, the predicted peak actually occurs. Forecast drift is important for understanding the epidemic development direction. The results of this work show that this approach has proven fruitful for modeling the coronavirus epidemic, not just for modeling home equipment. The success of the approach has been driven by contributions from scientists with domain-specific knowledge. Only this allowed us to fill in the general outline of the approach. This included definition of layers of secondary senses and secondary data, determination of key values, phase plane and concepts, typical behavior of the process, and transition to a new way of typical development of the process. After then it was not so difficult to build the whole system. Thinking about the application of this approach to the arms control, we can summarize. It is likely that the approach will prove fruitful for the arms control as well. The success of the approach application will depend on interaction with scientists deeply familiar with the arms control. If such a project is formed, then the development steps are clear, listed here. Our team is ready to participate in this project. Thank you for the attention. I am ready to answer your questions.